Hello, so I'm Sanjay Bhatnagar, and I'm very pleased to introduce our first speaker, Kumar Golap, who is a colleague of mine for many years and a friend of mine for even longer. Kumar grew up on the island of Mauritius, and after high school there, he attended Delhi University in India, where he completed the Bachelor of Science and Master of Science degrees in physics. He developed his interest in radio astronomy after attending a summer school on the topic at the Indian Institute of Science in Bangalore. In the early 90s, he joined the University of Mauritius for a PhD in physics. The research work for it was done in collaboration with the Raman Research Institute in Bangalore in India. During this time, the team built a radio telescope, believed to be the first in Africa, at 150 megahertz to make a survey of the southern hemisphere of the sky. After finishing his PhD, he joined the APES++ group, which subsequently became the CASA group, which is what it is now, at NRAO in Socorro, New Mexico, on a postdoctoral position in 1999. Since then, he has been a member of the scientific staff in Socorro, developing and maintaining the CASA software package, focusing mainly on the imaging issues with radio interferometers. Today, he'll talk to us about software systems used in radio astronomy.
So I'm Kumar Golap. So the title was a bit vague to work on. So what I'm going to try to do is kind of briefly explain what has driven software development in radio astronomy over time and with the problems that we have to solve. So I'll start by issuing an apology ahead of time, just because many of the things and interpretation are going to be mine, and my lack of knowledge might show in places. Also, as with many things in software, there is no absolute right or wrong, but many times choices are made. So I will try to avoid all this religious warfare that happens usually when we discuss software. When we talk about software systems in radio astronomy, I would say that there is a variety of systems, in fact. Over time, each observatory tends to develop its own tools to process data. But we can kind of notice that there is some kind of similar pattern that has evolved in this software. Also, one important thing, so one of the biggest success, I think, in radio astronomy or in astronomy in general is that from very early on, a well-defined data format was accepted to share data products, especially images, and that is FITS. Just to a lesser extent, this it followed for interferometer data, UV FITS and FITS IDI for VLBI interferometer data was defined so that we can transport between different packages that are written at different places. Over time, which radio interferometry kind of started in the late 60s or even earlier than that. But historically, the projects were kind of run by groups that did everything from the hardware to analyzing the data. And if software was ever needed, they would kind of do that themselves and write it. But in the 80s, observatories as service providers became a thing. So that observatories were kind of not developing science projects for themselves. They were providing service to other users who are not attached to the observatory. So when this happened, software had to be kind of provided along with the data to analyze these data that are given to the users outside of the observatory. So software development, as I said earlier, was kind of attached to the different observatories. So like there was a new star in Holland, APES here at NRAO, and Myriad in Australia. So I think around mid-90s or so, many of those observatories kind of joined into a consortium and tried to say, let's develop something that is common between all these. That kind of worked for some time, and then that dissolved in around the mid 2000, where the different observatories started doing their own thing again. But out of that, this consortium, at least a common software framework is still used, and some common basic data formats are still used. But the goal of all these is that we all tend to kind of to get the best data product with computation infrastructure that we can afford, and that's kind of what drives all of us. So the evolution of from instrument to science kind of thing, as I said initially, was kind of the software hardware was developed by the group that is doing the science. But then data as service came along. So then we had to provide some software with the data for the users to analyze and process the data. So the users in these cases at that point in time until today, this is what we do mostly. The user have to have a basic knowledge of the instrument, so that artifacts in the instrument that is due to instrument or interference and so on has to be understood when they are analyzing their images and so on. But as we are kind of in the process of moving away from that slowly, we are kind of getting along towards what we call science data ready products, where the user of the telescope in some sense doesn't need to know anything about the telescope behavior or the instrument behavior to analyze the data. So that the observatory has to kind of provide data products that are kind of proven to be kind of correct to a given level. So we are kind of between step 2 and 3 right now, especially at NRAO. In the next 2 slides, I'm going to kind of give a brief summary of what is the processing, that is the steps in processing that we do. The previous lectures have kind of given a lot of details on this. I'm just going to summarize it here a bit. So here on this equation here, the Vij is what we call the observed visibilities, which is basically the correlation between a pair of antennas, I and J. So that is the observed part, and the true, what we would like to have is the true visibilities. So that, but that is kind of corrupted by terms due to the antenna, which are attached errors due to the antenna, and also to the baseline based errors. And on top of that, there are 2 kinds of additive noise that are on it that comes along when we observe the visibilities. One is due to physics, which we can't remove. This is basically the sky temperature or the temperature of the amplifier at the antenna will introduce noise, and that is just something we can't remove. But there is another part that we could remove is, for example, errors that comes, for example, like interference. So this is, when we do calibration and flagging, what we can try to do is kind of correct for these antenna and baseline based errors and these additive term that we could remove. And once we do this, we will get what we call the corrected visibilities, which then we go to the next stage. We kind of invert the set of corrected visibilities with some weights to get a dirty image. That dirty image, we can consider it to be the recoverable sky model that we want, that the user want. But that is kind of convolved with what we call the point spread function. The point spread function is basically the inversion of the weight, the set of weights we used. And when I said the set of weights, it's also our sampling function is in that. So, so basically, these are the, this is kind of what we do. And then all the computation is to kind of do this kind of correction and this inversion stage. So through time at the VLA, the initial calibration earlier on was done as a part of the backend. That is, the data, whenever it came out of the telescope, the correlator, it was kind of pre-calibrated. And then this data was provided to the users to kind of, they did the flagging, imaging, and and calibration in stages. We moved afterwards to kind of providing the raw data, and then all the software that can do the calibration and imaging, so that the observer can recover their model sky that they want to use to do their science. And that was provided in software like APES. So over time, we have moved to kind of provide kind of pipeline processing or scripts that set a series of these different tasks in line to kind of provide reasonable calibrated products to the scientists, that they don't need to do that themselves. So then they can now just do the imaging part. And we are in the process of moving to, as I said earlier, to kind of provide directly science-ready data products, so that the user need not know anything about interferometer and all kinds of radio astronomy problem of antennas and so on by themselves, but they can just analyze the image and get to do their science directly. So as I said, we are kind of in between these steps, stage 3 and 4 right now in our development. The software itself in its design, so initially it was like little programs that everybody wrote to do some specific things. And then with data as service, we had to kind of have some kind of uniformity about these different executables and so on. So then we had kind of a similar kind of interface for all the tasks that are used to kind of process the data. And these kind of tasks were provided into a software package, like for example, APES. And in the late 90s, when the popularity of MATLAB started taking off, where people, scientists were more want to kind of have access to the data, and they can kind of play with their own algorithm. The toolkit package, the toolkit design kind of thing was thought to be the way to go. So APES++ and early CASA decided to write software such that the user can now have access at different level to the data, and they can use their own way of processing. So, but interestingly, this didn't catch on in the early 2000s for the radio astronomy users. So that kind of failure led to the fact that we repackaged all these toolkits that were available in the CASA and made them look like tasks just like in the previous packages and the earlier packages, so that it is kind of canned and fewer availability to kind of to access the data. Although the toolkit level of things is still available, most users tend to use the tasks. So, and the last decade, Python as a common user platform has become very popular. And the toolkit format of accessing and so on is kind of getting back, and then especially over the last few years, we can see that the success of AstroPy is kind of showing that. And more recently, we are kind of moving towards using a lot of other packages that are available in other scientific and technical fields for scalability and IO manipulation and so on. So this is the task-based design of the mid-80s and so on. So this is APES, but Myriad and other packages had a similar design. So basically the user would interact at a command line or interface that is provided, which will you'll have available all the tasks that are canned to do certain specific processes. and then they can either save it in one form or the other or view it. For CASA, that was slightly different in the sense that we initially provided these two levels of where either the user can have access directly to the data onto the command line interface, which now is Python, and or we provided some tools to do the inversion and calibration, and then they can kind of play with that in their own fashion to kind of make their own canned task. That didn't, as I said, that didn't work very well. So then the tasks were kind of defined specifically to kind of can these tools so that you do very specific tasks for imaging and calibration and flagging and so on. And on top of that, now we provide pipelines or guided reduction where you basically, the user basically put in the data, and then what they get out are science products that they can kind of start analyzing and do the science on. The battle has been is over time in that the problem that we've been tackling is we have to kind of adjust with between CPU cycle, the data transport, and the memory available. And I quote Eric Greisens from a paper he published in 1988, where he says that the VLA is capable of producing data at rates that would overwhelm the supercomputers of 1988, yet say those of 1978, where the first data was collected at the VLA. And this is so true today. We tend to build and design observatories and radio astronomy instruments, which are well ahead of the computation capabilities that we have today. And so the bet is that in the future, we will keep developing algorithm and hardware will allow us to solve the problem. So the square kilometer array, for example, which is kind of under phase 1 construction, I remember when it was designed, with a different kind of problem, imaging problem it had, we estimated that we would have to need a little nuclear reactor to kind of power the computers to reduce that data at that time. But now this is no longer true because the advent of GPUs and FPGAs has made the SK kind of more tractable, and it is kind of looking very doable now. So basically, I'll give you two examples of how in radio astronomy historically we kind of tweak our algorithm so that we kind of make the best use of the computer resources we had at the time. So for example, in the deconvolution stage of the imaging stage, there is an algorithm we use which called Hogg-Bound deconvolution. This involves basically subtracting, you look at a peak, and then you subtract a small fraction of the PSF from that peak, and then you locate the next peak. So every such subtraction, say you have images of n pixels, it will involve n operations because you have to subtract all these pixels. And you will have to keep kind of 2n pixels in memory. And say you find 1,000 such components, so this will involve like 1,000 times n operations and 2n pixels in memory. So the clock algorithm optimizes this so that to make, because at the time when this started being used, a memory and CPU cycle were very expensive. So to do that, then the tweak that Barry Clark did on this was to kind of, instead of doing the whole subtraction of the images at every component, you subtract only a small patch of 50 pixel by 50 pixel. And you do that for a few of them. So in that process there, you have to have only 2 patches of 50 by 50 pixels in memory. And the operations involve only 50 by 50, that is pixels that you have to subtract. So, and then after doing this for a number of times, you kind of Fourier transform all these components you got, and then you go and subtract it in the graded visibilities. And then you Fourier transform that back to get the to get the next set of residual, and then you continue doing that. So if you do that in there's two major cycle stages, then as you can see, this is the number of operation that will be needed in this kind of algorithm, tweak of algorithm, and the fact that you keep much less memory, that is much less pixels in memory at any given time. So this was kind of to save on computation and memory, because that was the most quite expensive at the time when these were being initially done. So another example of how we adapted to kind of, we try to get the best images we can and adapt the algorithm to do that, is the W correction problem. So the relationship between sky, this is a one-dimensional equation I'm writing here, but it is a two-dimensional one, just to simplify it. I is the image that we want to recover, and V is the visibilities that we observe at a pair of antenna. This is the full equation that relates them. It is not really a Fourier transform, if you look at it like as it is, but we kind of coerce it to become a Fourier transform so that then we can invert it. So, and many times we kind of, the way we coerce it is to make sure that this term W is very small. But in many cases, this is not always the case. You cannot coerce it to be that way. So for low frequency and wide field imaging, that's what we'll have to invert this equation properly, or at least in some to some approximation. So there are two ways I'll mention here. One is called faceting. So you break that integral into a set of smaller pieces of integral. So you kind of make small patches in the sky, or small facets. And then you sum all these facets to make this whole image you want to recover. So then this integral, you break it into a sum of smaller integrals. And that does, each of the smaller integrals now looks close, a bit more like a Fourier transform. So this processing has to be done. You have to to do that, you have to iterate through the whole visibility data for each facet to achieve that. Another way to achieve this is, if you look at this equation and you kind of move all these, the W term and all the extra term here into a function GWL, then the equation looks like this. And this is kind of, you have a multiplication in this domain, then you can find a convolution function so that you convolve with the visibility, so that this, on the other side, you can make this, coerce this into look like a Fourier transform. So this is the way we kind of solve for the W problem, is by convolving for a set with a set of convolution function, the visibilities, so that we can then do a Fourier transform to achieve, to regain the image. So this algorithm, in this one, you don't need to go through the data multiple times. So here's kind of the thing is, for using faceting, you have smaller sets of images in memory, but you have to do a multiple pass through the data. So the time taken to process the whole data starts getting proportional to, or is kind of highly dependent with the data volume you process. And as time went, this was very doable earlier on when we were dealing with a few gigabytes of data. Once it started crossing hundreds of gigabytes, then this started getting into days of having a one desktop to process, to do that imaging. So that's where then the W projection gets you again, but here you have a lot of memory you have to use. You keep the whole image into memory, but you do one pass through the data. So, and you also have to use a lot of convolution to do that. And some of the convolution are large, so memory is again an issue. But for large volume of data above 100 gigabytes or so, for the VLA, for example, it gives you an order of magnitude speed up. So with the cheaper compute cycles that we've been achieving, and we've been using multiprocessing and multi-threading in software. So in our software, we tend to use MPI and OpenMP to do that. And we are moving towards GPU, where it has been demonstrated that we can achieve like 2 orders of magnitude speed up for pure grading. There's a memo by Pokorny recently published about this. So this whack-a-mole contest between CPU, memory, and I/O continues. And right now, with the cheaper CPU, our processing and memory, and to some extent memory, a lot of the issue that is the slowness now is gone into the transport from storage to compute, and to memory and to compute. That has become the dominant factor. In the last couple of slides, I'll kind of mention where we're kind of looking forward, what we are experimenting with these days. Yeah. So we would like to kind of reduce the amount of code we maintain ourselves for, specifically for things that are used in common in the future by other domain too. So I/O and parallelization and so on, we don't need to we do want to kind of use what is available. So the other requirement would like to have scalability. That is, it's easily scaled to thousands of compute nodes, for example, or things like that. And also portability is becoming more important now, as we have a lot of different platforms that are coming up, like the chips, that is a system on chips coming up, and also the ARM processing CPUs and so on becoming cheaper, and with the GPUs and FPGAs and so on. And also we'd like to use other software packages that are being developed by other branches of science. So we have been developing a prototype infrastructure, which is based right now on using these are data format. And we are using Dask and Xarray to kind of do the processing. So with Dask, we kind of set up all our algorithm in a DAG. So once you are able to do that, then depending on what kind of infrastructure you have, how many nodes you have, the Dask will kind of use the infrastructure to kind of compute the different parts of the DAG over time and get you your result. So this is the part where the what we call the CASA next generation infrastructure, and this is kind of, we are experimenting right now. So this is very experimental, and we'll see how that works. So radio astronomy software for data reduction, I think, has always been behind the capabilities of telescope, and that is a fact. And over time, depending on the technologies we have, we kind of work on one of these or all of these to kind of achieve the best time and best quality of images or data products we can produce. So these three has been kind of, we keep hammering at these three, and maybe in the future it's maybe just two, because the development of in-place computation seems to be getting on now, so that the memory and data transport can be kind of merged into one issue. That's it, I think. Thank you.